Okay, back to dividing monomials. Here we are, part two. This is an idea that throws people off really badly, but if you stop and think about it, just apply some arithmetic to it. It's not too bad at all. It's not hard to believe at all. The concept says this to us. It says if we have a zero exponent, that is, if we have a to the zero power, its value is going to be equal to 1. Now, it's important to realize, a little asterisk here, a can't equal 0, and that will become clear to you in a second also, I hope. But let's look at this for a second. So I guess the first question I'd ask myself is, well, when would an exponent equal 0? And if you thought about it, let's look at this for a second. Let's say we have 2 to the third power. So 2 to the third power over 2 to the third power. If we're in 6th, 5th, 6th, 4th, whatever grade we're in, we'd have this, and we'd say, well, this is equal to 2 times 2 times 2, which is 8. And this is also, down here is the same number, so it would be equal to 8. And, of course, 8 over 8 is equal to 1. So how does that apply to what we're doing here? Well, we have this rule for exponents. This we say if we have a to the mth power over a to the nth power, its value is a to the m minus n. It's in the last video that we just did. And we proved that a bunch of different ways. Well, look at this for a second. Let's stick with the example that we have. We have 2 to the third over, not to the third, but yet 2 to the third power over 2 to the third power. And using this rule here, it would be 2 to the 3 minus 3 power, which would have to equal 2 to the 0 power. But we know arithmetically, recursively, that the answer here is 1. So hopefully this is providing some. Remember how these rules were made. The rules were made, people looked for patterns, and they looked for the pattern, and they tested the pattern over and over and over again. And if it turned out that the rule was always true, then they would turn it into a rule. And if there was some caveat, there was some problem with that rule, they would, and the problem was addressable, they could do something about it, they would notate that. So here's our notation here. Try another example. Take your own number, keep it small so you can see it easily, and then raise it to the same exponent. So maybe your number is, what was your number? 7? Okay, 7. So you had 7. I said, well, square 7. So you have 7 squared over 7 squared, which would equal what? 49 over 49. And, of course, 49 over 49 is unarguably 1, isn't it? Now go back and apply the rule of exponents, this rule up here that we had just gone over. And wouldn't that be the same as 7 to the 2 minus 2, which would be 7 to the 0? But we know arithmetically that the the answer was 1. So 7 to the 0 must be equal to 1. Why can't a equal 1? Because 0 over 0 to any power is undefined. We cannot have a 0 as the total of the denominator. It goes to undefined. And if you want to talk about that, please let me know. I'd be glad to talk about that. But that's why a cannot equal 1. So let's see the problem that they throw out there for us. They throw out to us, negative 0.25 to the 0 power equals 1. They don't offer us any proof of it. They don't offer us any proof. We just have to buy into it. The proof is what I offered you, which is this proof up here. So it's one of those rules that a lot of professors and teachers don't really want to talk about the rule too much, because how would you prove it? Well, you'd prove it recursively. You would prove it by saying, isn't this a fact? So take some examples. And that's why any number, a, raised to the 0 power is equal to 1. Please write that down, and also remember that works for every number except for 0. 0 to the 0 power is not equal to 1. Okay. Then they wanted to talk about, in the table, they also want to talk about negative exponents. So I'd like to address negative exponents myself. So let's look at negative exponents. So negative exponents. Negative exponents. This is something, if I can get you to say this 20 times in your head, it will lead you straight to victory, because I can see how a person might think this was true. If I say that I'm going to raise something to a negative exponent, like a to the negative nth power, I can see how a person might think that this was going to cause a negative number. Negative x stay with me, this is crucial. Negative exponents don't cause negative numbers. Negative exponents cause fractions. Stop the video, write that down. Negative exponents cause fractions. Negative exponents cause fractions. So what the author wants us to know is this. The author says, well, this is what I want you to know, that if you have a to the negative n, what you really have is a is 1 over a to the positive n power. And man, that throws me off a little bit also, because I can't get my head around that. But I can if I look at this arithmetically. So arithmetically, let's take a look at when would that be true. How about this? How about 5 over 5 squared? So we'll do a little bit of 6th grade math here, and we'll say, well, that's the same as 5 over 25, isn't it? And then we'll simplify that, and we'll get 1 over 5. Right? This is true, right? This is not arguable, right? This is declarative. We can declare this with some confidence that this is true. So the question is, why is this? So why is this true? And I'm suggesting to you that this is true because of that. So let's take a look at it for a second. 5 is 5 to what power? We've talked about this, and you're right, it's 5 to the first power. Anytime we have a number and we cannot see an exponent assigned to it, like this one, we assume that there's a 1 here in the same way that we assume that this is positive 7. Why is this positive 7? Because there's no negative sign. Why is this 5 to the first power? Because there's no exponent assigned to it. So we have to assume, it's assumptive math here, we have to assume that this is a 1 here. So using this rule here, a to the m over a to the n, we talked about this in the last video, this is to the nth power here, is equal to a to the m minus n power. Then if we do that, we get 5, right? They have the same basis, 5 to the 1 minus 2, 1 minus 2 is equal to 5 to the negative 1. But we know that the truth of this math is that it equals 1/5. So what this is a simple explanation of how you cure this. Because that's true, isn't it? Any number over 1 is just itself, isn't it? And we're going to take the reciprocal of this number. That is to say that this goes to the top, and this 5 to the first goes to the bottom. But as it comes down, the negative sign goes away, it's cured, and becomes this. And that's the answer that we're expecting, isn't it? Okay. All right, let's take a really quick example from the book, and let's see if we can make some sense of that for negative exponents. And we would have b squared. So here's our example from the book. Example here: b squared over b to the 5th is equal to, well, right, b, we're going to use the rule for dividing exponents. We have same basis, so we subtract 2 minus 5, don't we? So 2 minus 5. Well, 2 minus 5 is b to the negative 3rd power, isn't it? Again, what are we going to do here? Take a look. This is just what I'm seeing in my mind. I'm like, you know what, that helps me to see that better. And I'm going to take its reciprocal and flip that over and get 1. This 1 is this one. This solidus or fraction bar is this one. And b to the negative 3rd becomes b to the positive 3rd power. We're going to have lots of time to work on this, but this is something that you're going to have to get your head wrapped around, okay, guys? Good work. Hope you're taking good notes and you're practicing this stuff.